All right, good morning, guys. I wanted to make a video about water potential, which is the topic that we're going to be learning about next. So let's start with the definition of water potential. Water potential is a measure of how likely it is for water to move from one location to another. Water, just like other things, moves from an area of high concentration to an area of low concentration. Right? So if your water potential value is low, and it can be negative, it'll move in that direction. All right, so water potential, it can be positive, it can be negative, it can be zero, but water is always going to move to the lower number. All right. So there are two equations that we're going to need to know. The first is that water potential is equal to solute potential plus pressure potential. All right. The equations are in blue on the worksheet right here. I'm going to highlight it, underline it in red. So we have this Greek symbol called psi. It kind of looks like the experiment that is used for these water potential problems. That's how I remember it. Okay, so if you notice here, we have this experiment showing how water potential works. The Greek symbol kind of looks like that. Maybe that's why they chose it. I don't know. Anyway, so the equation is solute potential plus pressure potential equals water potential. We also have another equation that's going to be very important for these types of problems, and it is that solute potential is equal to negative I CRT. I being the ionization constant, C being the molar concentration, R being the pressure constant, which is always 0.0831, and T being temperature in Kelvin. A couple important things here, okay? Depending on your solute, it's going to have a different ionization constant. Sucrose is 1, glucose is 1, and salt, sodium chloride, is 2. The pressure for an open container is always 0, and a plant that is under turgor pressure is 1. Right? So the first video here is just about kind of conceptual understanding of this topic, water potential, okay? So right here we got it's a U-shaped test tube. Very interesting, right? Well, there's more solute on the right side than there are on the left side. And because this is separated by this semi-permeable membrane, right here, see the semi-permeable membrane? Water is the only thing that can actually go through that membrane. Right? And what water is wanting to do is it wants it to be at equilibrium. And the only way for that to happen is for the water to move towards the right. Right? Which, if you notice, the water has actually risen. Right? It's actually gone up. Okay? And so that's the experiment they typically use for these types of problems. And very interestingly, it looks like that Greek letter psi. All right, over here we have something different that has happened, and that is the experimenter person has put this plunger type tool on top of the right hand tube and is actually now pressing it down, applying pressure, okay? And we know that water potential is equal to solute potential plus pressure potential, right? So when they apply that pressure, the water goes boop, back the other direction. All right, I can actually draw that in for you. Okay, so we've got the membrane there, and now the water is going to go this way. All right, back to the other side. I didn't know this. This is something that I'm kind of just guessing from what the picture says. This is labeled as reverse osmosis, so maybe that's how that's done. Okay. We got 20 seconds left in the video. Take a look at this picture here. Okay, this is of plants. Obviously, if the water potential inside the plant is higher than outside, water will leave the plant and it will droop. Same for animal cells. Okay, so there you go. Water potential.